So what is a phase transition? Well, we see them every day. We're pretty familiar with them, actually. You see water evaporate, that's a phase transition from liquid to gas. You see water boil, same thing. You are probably noticing some frozen water outside right now that's in a particular crystal formation that's a function of how the atmosphere and climatic conditions are. Um, so snow is also a phase transition. And you might wonder, why do phase transitions happen? Why does water sometimes want to be liquid, and why does it sometimes want to be solid or gas? Well, these are the kind of questions that I'm going to be answering with this. And I'm going to go a little bit further and generalize the notion of an equilibrium phase transition, which is the class of phase transitions I was just talking about. We're also going to talk about non-equilibrium phase transitions, that are phase transitions that occur in matter that have the same mathematical signatures as equilibrium phase transitions, but occur in dynamic systems. You can think about this as an electrostatic situation in physics, the situation where there are a configuration of charges and the charges are not moving at all. That is technically a static situation and is technically a configuration. But you can also have what's known as a steady state configuration, which is where there's a steady current. That is, the charges are moving, but they're moving at a constant state, a constant speed, and that's dynamic yet static. It's the current is constant, and the magnetic field doesn't change, even though the charges are moving. So in the electrostatic situation, you can think of as an equilibrium phase transition. That is, the configuration is not moving, it's staying at equilibrium, the macroscopic aspects of it at least. The molecules are still moving around even at equilibrium, but the macroscopic quantities are fixed at equilibrium. And I'm going to talk about why and how they're fixed at equilibrium. But in non-equilibrium phase transitions, stuff can still be moving around. For example, traffic flow can be in a phase of either, imagine an on-ramp and an off-ramp, and the on-ramp and off-ramp are on-ramping cars and off-ramping cars at the same speed. Obviously, then you just kind of drive like you normally drive at the same at whatever speed you want to drive, the speed limit, or if you're feeling risky, a little bit higher than that. But the idea is that that's a phase of that traffic. Things are still moving around, things are still changing. It's not like ice where it's just a crystal. It's a constant movement of traffic. And if you tweak certain parameters, for example, with ice, if you tweak the temperature or the pressure, you'll see a phase transition. It will go from liquid to gas. And I'm going to talk about in this presentation why, under those conditions, it prefers to be in a certain state over another state at all. But the same thing happens in traffic. If you change the rate at which cars are off-ramping, that is leaving the highway, or you change the rate at which they're on-ramping, that is coming onto the highway, you can induce a phase transition the same way you would if you change temperature or pressure of water. So the different phases would be traffic jam, critical, where everyone's just barely making it, but cars are not actually having to put the brakes on at all because the traffic is continuously flowing. And then traffic jam, where cars actually have to slow down. So you actually are more familiar with phase transitions than you think you are. All right, so what is this slide here? Well, it's certainly a title slide, and it's very colorful to draw the attention, to keep everyone interested. There's not going to be much color throughout the rest of this presentation, so enjoy these primary colors while you still can. So non-equilibrium phase transitions on networks specifically, yes, they are going to be on networks. That's the model we're going to be using, but just think non-equilibrium phase transitions. And when dynamics become geometry, that's kind of an obfuscated title. Essentially, the idea is that things are moving in non-equilibrium phase transition, like I just talked about, whereas it's kind of a geometrical consideration why equilibrium phases settle where they settle. So what is this mysterious thing here, this very fancy looking O that isn't quite closed? What is this here? Okay, don't worry about that. This mouse and this program don't play well. So this O is what's known as an order parameter. And this lambda here is known as a control parameter. Now, if we're talking about the water example that I went over, the order parameter would be the orderliness of the molecules. And the control parameter would be something like temperature or pressure. There can be multiple control parameters. But for simplicity's sake, we're going to focus on situations where only one is varying at a time. So in the case of water, as we adjust the temperature, this order parameter will change. And an order parameter is actually relatively simple. It has binary behavior. It's either 0 or it's non-zero. Water is a little complicated to think about, but if you think about liquid water, the molecules are just randomly jostling around. They can go anywhere. They're kind of like this. I have animations later to show that exactly. But for now, you're just going to have to settle for my fingers. When they're in the ice form, the solid form, or snowflakes, they're locked into a crystal. They're not moving. They're slightly vibrating a little bit, like they're phonons and stuff, but they're locked into a certain crystalline ordered arrangement. So that's the order parameter. The order parameter specifically is the Fourier transform of the position of the molecules, which is basically 0 if it's totally random, and it's non-zero if there is some sort of order it's picking up on. So if it's in a crystal, there is an order to pick up on. There's a lattice parameter, which is the distance between the molecules. And for example, in the case of ice and snowflakes, it's locked into a hexagon. So a Fourier transform will pick up on the hexagonal structure. It's not totally random like it would be in liquid water. So this order parameter is non-zero. What's another example of an order parameter in a simpler system? Think about a magnet. If you take a magnet off your fridge right now and you heat it up, it's not going to attract metal to it anymore. That's because it underwent a phase transition. It was known as the Curie temperature. It's no longer magnetized. So if you think about a magnet, it's actually made up of a lot of little electrons, each of which have what's known as a spin moment. It's really their total angular momentum, but a spinning current like this induces a magnetic field like this. And you might wonder, well, okay, where's the macroscopic magnetic field coming from? And why is it always magnetized? Well, it's because each of these electrons have a degree of freedom to point that magnetic field wherever they want, depending on where they're oriented. And if you introduce enough heat and things are jostling around enough, you kind of knock those spins off of their axis. You knock them out of their alignment. So if you heat a magnet up enough, those spins are no longer aligned with each other. And if that's the case, then it's not magnetized because all the little magnetic moments are canceling each other out. So that's a phase transition, a magnetized ferromagnet to a unmagnetized ferromagnet at the Curie temperature. So I can kind of give you a flavor of that. And what's this exponent over here, this B? Well, it turns out that near criticality, this order parameter scales really cleanly and nicely as this is the critical temperature here. And this is, this is what's known as, sorry, my pen stopped working. So you're just going to have to imagine me drawing a circle around that little beta there. Oh, wow, that's interesting. It's working on the presentation, but it's not working on my screen. All right, whatever. The idea is that critical temperature is the Curie temperature in the case of the magnet. It's the freezing point in the case of water. So when that hits 0, we see a divergence because this is typically negative. So it's 1 over whatever's in those little absolute value brackets there. So it blows up and goes to infinity this is the order parameter. We're not talking about the free energy here. Ignore what I just said about singularities and things like that. The order parameter cleanly varies as this function here of the control parameter. So that's very nice. And this is kind of getting to the heart of the concept of universality, which is phase transitions can be roughly grouped into these universality classes. Similar phase transitions happen similar ways, and they all have the same critical exponents. What's interesting is that the microscopic details, where every atom is, how fast every atom is moving, what configuration every single atom is in, are all washed out. And these critical exponents remain for a large class of different models and different physical systems that all have very, very different microscopic details. That's universality, and it's really the heart of phase transition. So I really want you to remember it. Excuse me for a second, I have to let my mouse dry. Okay, so I really want you to remember that. That's the heart of universality. And what's cool and binding between non-equilibrium and equilibrium is that non-equilibrium phase transitions also show these same kind of signatures. They have their own critical exponents, which is probably the cleanest way to see the transition. So this kind of explains what I was just talking about. Oh, my pen's back, awesome. So we have this control parameter here. Think of it as temperature, pressure, something like that. And as we vary it, we get this relationship. So the order parameter and control parameter, I already told you what those were. Quick refresher, the order parameter in the case of magnets are the magnetization. In other words, if I have a magnet and I put some ferromagnetic material by it, like iron, how strongly does it attract that ferromagnetic material? That's the order parameter, right? Magnetization. If I heat it up enough, it goes to 0. The magnet just doesn't work anymore. In terms of temperature, it's the orderedness of the atoms or the molecules. So in ice, they're locked into an ordered position. They're periodic. They're predictable. There's one every A, where A is the lattice structure, and we definitely know they're hexagons. Different crystals have different shapes, but they all have an order to them that Fourier transformation is going to pick up on. So the control parameter is something like temperature in case of both the magnet and the water, which is why I guess I subconsciously picked that example. Then we have 2 more things that are mentioned here. We have what's known as the correlation length, which is really fascinating, actually. If we have some molecules that are jostling around in a big enough volume, we want the quantity that tells us how far out can I go from this molecule? How far out can I go when this molecule is not affecting stuff out here anymore? In other words, everything that's happening a certain distance away is no longer a function of what that molecule is doing. So the idea is, how long out do correlations last? You can think about this in terms of magnetism or gravity or electrostatics, whatever. If you zoom out far enough, the field gets weaker and weaker and weaker, and eventually it doesn't matter anymore. So that's really the microscopic origin of why that's happening. But the idea is we can kind of coarse grain volumes into little sectors, little regions, little bubbles where correlations still matter. So if I'm 5 feet away from this molecule, I am actually interacting with it. It does affect me. There's cause and effect between us. So if it goes here, maybe that forces me to go here. But if I'm like 30 miles away from it or something like that, I'm not even going to notice it. I'm not even going to know it's there, or our behavior is completely unrelated. That's the idea of correlation length. And a key signature of phase transitions is that near the critical temperature, near the freezing point, near the boiling point, near the Curie temperature where something demagnetizes, this correlation length explodes. It blows up. It goes to infinity. That is, there is no longer a way to coarse grain and say, okay, I can divide this into 5 feet by 5 feet cells. And each of these cells, or 5 by 5 by 5 if we're in 3D, each of these cells is where correlations matter. No, you can't do that. I actually have animations to show you later on that. But the idea is you can't do that because correlation length is the entire volume. In other words, you can't go far enough out to no longer be correlated with that molecule or that atom or that particle, whatever it is. Yeah, that's literally what I just said. So we can move to the next slide, I suppose. Right, the control parameter. Yeah, it's tunable in the sense that you can control it in a laboratory if you want, or nature controls it if we're talking about something like temperature or pressure. The order parameter I just talked about. It can be any of these things. This is either probability density in terms of how many molecules are in one area, or this row could be the orderedness of water molecules, something like that, but it generally means density. These little angular brackets mean expected value of. That is, if you take this quantity, like let's say magnetization, the magnetization is pointing up here, it's pointing down here, it's pointing down here, it's still pointing down there. Over a large region of space or some region of space, you take an average, or you can do it over time. You can say it's here and it's moving and it's doing this and it's doing this. What's its average over time? That's what those angular brackets mean. And I just talked about scaling at criticality. At the critical point where a phase transition is about to happen, you get this exact form here. And notice that it's a negative, meaning it's 1 over whatever this V is. So these power law statistics emerge, which is nice. The reason that these power law statistics emerge is at a very deep level renormalization, but essentially there's an analytic part to the free energy, and there's a non-analytic part that has these kinds of problems at phase transitions. So that's the part that's giving you these universal exponents. Okay, so here we have kind of an animation. Hopefully it wants to play. You tell I'm not very well versed in Microsoft PowerPoint. Nope, that's not what I wanted at all. There we go. All right. It's not playing on the screen, is it? Let me check if it's actually. It is playing. Okay, I just can't see it. So this introduces a unique challenge for me. Okay, so no. Spacebar is doing different things now than it did before. Okay, here we go. So we have this control parameter here. That's the temperature, something like temperature or pressure. And we have this order parameter here. That's something like magnetization or the orderedness of the molecules. So something that's a macroscopic quantity. It's a function of a lot of atoms or particles or molecules. Okay, something like magnetization is not defined at the microscopic level. They're like little moments. At the macroscopic level, what we perceive at our anthropic scales, something we can measure with a thermometer, temperature, pressure, how strong this magnet is attracting this other magnet, those are macroscopic quantities. Microscopic quantities are how the individual atoms or molecules or microscopic things are acting. We're not always concerned with those, and sometimes we just ignore them. They're not interesting, right? If I have some water in an industrial lab, we actually don't care where the atoms are. We don't care. What we care about is this vial of liquid a solid? Is it a liquid? Is it a gas? What's its temperature? What's its pressure? Can we drink it? Is it safe to drink? All that kind of stuff are all macroscopic quantities. We're actually not too interested in where the particular atoms are or what they're doing. So then we have this scaling here. This is the correlation length, what I was talking about before. Um, you notice each of these little like black bubbles here. Each of these little black bubbles here is the correlation length. It's a volume around the correlation length. So I really wish this animation would play. There, okay, there we go. So let's just take this one as an example, and I won't touch anything so that it keeps playing. So we see this control parameter varying. TC, this is the critical point. It's the freezing point. It's the Curie temperature, whatever it is. And we see that this here, this magnetization, the macroscopic quantity we're interested in, we can actually measure. We see that it takes this kind of pattern, that it's non-zero here in the disordered phase. And in the ordered phase, it becomes zero. Sorry, it's zero in the disordered phase. Disordered, thinking about little electrons with their magnetic moments all kind of over the place, pointing different directions. Whereas when they're ordered, they're all pointing the same way. That's the ordered phase. It's the crystalline phase in solids. That's when it's non-zero. You can actually attract a magnet with another magnet when it's magnetized. So you see this correlation length here on the right. That's each one of these little black cells is how far out the interactions still matter. In other words, if I have a little particle in here and I'm out here, they don't relate to each other at all. There's no cause and effect at all between these two things. But if there are two particles that are within the same little black blotch here, they're still affecting each other. Yeah, this presentation really absolutely does not want to start. That's okay. So, oh, good. The animations that I actually made have these little things on them. Yeah, so that's basically what I just said before, but depicted in animation form. All right, so this is interesting. Let's say I have some water in a glass. How much water do I need for it to actually undergo a phase transition? Well, if I have only 2 molecules of water, the phase transition is actually not well defined. Only as L goes to infinity, which is the size of the lattice, do phase transitions actually occur. They still happen with smaller amount of molecules, but they're not true phase transitions because they're not singularities. They're not sudden jumps. They happen continuously, smoothly, and nicely. So as you see in this, as the lattice gets bigger and bigger, this transition between the ordered state and the disordered state gets sharper and sharper until eventually it's an actual discontinuity. So that's important to remember. All right, so in this section, we're going to talk about equilibrium phase transitions. Those are the ones you're used to. Think water, think magnets, think all these kinds of things. Nothing too exotic. So why does water like to be ice sometimes, and why does it like to be water or gas some other times? Well, there's a very solid physical bedrock that explains this, and it's this idea of maximizing entropy. But sometimes we can't just freely maximize entropy. Sometimes there's an energy conservation constraint. Sometimes your system is in contact with a heat bath. Sometimes your system is constrained to be at a constant temperature. So under those conditions, the second law of thermodynamics is always correct. You're always trying to maximize entropy. It only increases. But you also have to satisfy that constraint with an additional constraint, which is that the energy is of a certain constant value. Energy can't just pop in out of nowhere. So that's where we get this more complicated kind of mathematics that comes from. You can see it says on the left column there, an isolated system maximizes S of E as entropy. That's the formula for entropy. It's literally just the probability of a given microstate times the log of the probability of a given microstate. That's called Shannon entropy. It pops up all over the place, not just in thermodynamics, but it pops up in information theory. It pops up in computer science. It pops up in linguistics a lot. It defines the amount of information a channel like a phone line or a cable line can contain and transmit. Fascinating quantity. Maybe that's a topic for another lecture some other time. But you want to maximize it. This is kind of the heart of why systems act the way they do macroscopically and microscopically. In other words, they want to be in a configuration that maximizes entropy. And again, that's kind of like a cute phrasing, right? Like wants to be, like a physical system wants to be something. That shorthand for the probability of it being in that state is astronomically higher than its probability of being in another state. So there's a certain configuration of atoms and molecules that is of a certain entropy. It can be in a lower entropy state, but it would literally take longer than the age of the universe for us to see something like that. Think about a casino with like an infinite number of cards or something like that. How long would it take? There's only 1 2 in the entire deck of cards, and the deck of cards is of an astronomical size. How long would it take you to see a 2? Longer than the age of the universe if we make the deck of cards big enough. So that's kind of the situation with entropy. We can see entropy minimization, entropy going lower is actually possible, but you'd have to sit there longer than the age of the universe to see a glass of water spontaneously do something that lowers its entropy. So we see here that, and the idea here is that, remember the macroscopic quantity as I was talking about before, like magnetization or temperature or something like that. Each one of those does not correspond to a unique microstate. That is, there are many ways to arrange these atoms in many different ways with many different velocities, and they'll all have the same temperature or same magnetization. So many macrostates, or one macrostate rather, one temperature, corresponds to a lot of different microstates. And the temperature or the magnetization or the macrostate that has the most microstates that correspond to it has the highest entropy. That's what that means. That's really all entropy actually means in a thermodynamic context, at least, is that one macrostate has an enormous amount. I mean, big numbers where you need to use like Stirling's approximation to even put them into computers. Computers can't handle them. That's how big these numbers are. Probability of seeing or number of microstates corresponding to this macrostate versus a different macrostate with way less microstates corresponding to it. So if each of these microstates has an equal probability, which we do assume in the isolated system at least, then the chances of seeing that macrostate with a very high entropy is almost certain. It's basically probability of 1. So that's a quick primer on entropy and why we want to maximize it. And then the second constraint is that we want energy to be of a certain value. So that gives us this kind of like Maxwell-Boltzmann configuration. You can Google thermodynamics and velocity distributions if you want. But essentially, the system sort of settles into an equilibrium where not much else is kind of happening. So ice is ice unless the temperature changes. That's kind of the idea. That's an equilibrium state. So these systems spontaneously and probabilistically kind of settle into this state. There's no force forcing them to do it or anything like that. Not like us where we're kept on Earth by gravity. It's just the laws of probability that keep ice as ice. So we see the free energy. Yeah, that's a very important concept. So F is the free energy. That's essentially H, the expectation value of H, which is the expectation value of the Hamiltonian, is just energy. Minus T of S, which accounts for entropy. So you want to, the same thing as of maximizing entropy subject to these energy constraints is mathematically this. H minus Ts, you want to minimize that. That's called the free energy. That's basically just you do the math on what maximizes entropy while keeping this energy of a certain value, and this kind of pops out this free energy. That's all it is. So that's what determines equilibrium. This is just saying the same thing over again, basically. Lagrange multipliers is the actual way we actually calculate what free energy looks like. And here, yeah, this is the actual solution. It's an exponential in beta, which is 1 over kb, the Boltzmann constant, times temperature. So you see temperature affects the probability of each given state. PC is the probability of being in a given microscopic configuration. Okay, so now we're going to talk about what the free energy actually looks like. So I talked about this free energy thing, but we don't know what it actually looks like. And we're going to turn to Landau, Ginzburg, Wilson theory for this. We're going to start with the Landau, then we're going to go to the Ginzburg, and then we're going to go to the Wilson. So this is skipping ahead. Okay, Landau theory. Landau basically told us that we have this free energy, and we're going to make a quick assumption about this free energy. It's the same at every single point in space. That's the tacit assumption we're making here. And then we're going to form this free energy. And this free energy you can see here in the third line there on the left. It's this kind of psi thing. And that psi is the macroscopic quantity, like magnetization or something like that. It's the order parameter. And we said the free energy has to be of this form simply by symmetry considerations. So just because of the symmetry of the system, we know that it has to be of this kind of form. And this is the form, particularly we eliminate the linear and quadratic and odd, or not quadratic, cubic. We eliminate the odd order terms and second order phase transitions because it's simply the physics would violate laws of physics for it to have those terms. It wouldn't make any kind of sense. This is what's known as a mean field theory, yeah, because we're assuming that the fluctuations spatially are much less than a certain physical constant or physical parameter. Yeah, so this is an animation. This is a good animation. Okay, so remember, ordered state, disordered state. And the quantity that's varying over time, this blue line is the Landau free energy, and I'm changing the control parameter. Just imagine this T as temperature. So we're in the disordered state. In a magnet, that would be demagnetized, it's too hot. And in terms of water, that would be the liquid state. So we're going to move from the disordered state. This is the minimum of the free energy. Remember that all that entropy stuff I talked about, subject to those constraints, you want to minimize free energy. So the physical system you actually see in nature is the one at the minimum, which is where that little orange point is. It's the minimum of the free energy. That's what you'll actually see. But you can alter something like temperature to change where that minimum actually shows up. Okay, I don't know why it's misbehaving here. Okay, here we go. Watch. So we start as water, we change the temperature, and the free energy landscape changes. And in the ordered state, we see what's known as spontaneous symmetry breaking. You might have heard that term before. But essentially, the system now has two minima, and it has to just spontaneously break symmetry and choose one of the minima. In terms of a magnet, what this would correspond to is if the magnet is ordered, it can be all the spins can line up, or all the spins can line up down. Those are those two little orange dots. So nature has to choose negative M or M. It just spontaneously does it. And lots of interesting stuff comes out of that, like phonons and particles and Goldstone bosons and all that. But we're not going to talk about this in this presentation. Feel free to do further reading on that. But all right, now we're going to add the Landau part to the Ginzburg-Landau-Wilson theory. Functional free energy. Now we're gonna remove that assumption we had before that it doesn't depend on space, and we're gonna say, okay, yeah, we know that in real life the field depends on space. The magnetization over here is different than the magnetization over here. It can be. Why not? I mean, nature can vary spatially. So you can have a different magnetization in this cluster and all the way 5 feet to the left. That cluster is going to have a different magnetization. So that's the Ginzburg part of Ginzburg-Landau-Wilson. And now we're going to put this gradient term in. Don't worry about what a gradient is or what a gradient term means. What it actually does is it penalizes spatial fluctuations. So the free energy goes up if spatially you fluctuate too much your magnetic field. So that the incentive is to minimize the free energy. So you don't want to vary too much. That's kind of what it actually does. And again, this is still mean field. We're assuming the fluctuations are within a tolerable bound. This is the actual quantitative way to see that the fluctuations are of a bound. This means the critical value of that field. And you can see we're only keeping the even terms in this because we're talking about second order phase transitions here. They would violate symmetry of the linear terms and the rest. Okay, now the fun part, Wilson and renormalization groups. Why we get these universal constants at all. So let me find the thing I made about, no, I think this is it. Yeah, perfect. All right, so this is how the renormalization group works. Okay, no, that's not what I wanted. Oh, here we go. Okay, yeah, so this is the process of, you probably heard the term renormalization before. It pops up all over the place in particle theory and things like that. It also is very useful here. We kind of borrowed their toolkit. Right, so you start with a field theory, and it has these couplings. So the free energy is the quantity of interest here that we want to minimize, and that governs the system and forces it into a certain state. So you see the free energy is an integral, which is just a fancy sum over functions of this order parameter here. And this order parameter has these little coefficients before it. And these coefficients are what is known as coupling constants. They're little dials you can control in the system that tell you, for example, how annoyed the system is when you change the spatial variation. So how sensitive is the system to a change in spatial variation? How rigid is the system? That's the idea of if you change this over here and change that over there, how much will that lower the free energy? There's other couplings all over the place that kind of control those kinds of conditions of the theory, right? Think about mass. Okay, F equals ma. M is a coupling constant. It couples mass to the force. So the idea is these constants kind of change as you renormalize, but you start with a certain configuration in this space, which is I think coarse graining is step 2. We have it on this. It's just explaining what coupling space is. Basically, it's the constants and the coefficients that are sort of like dials in the theory that control the theory's sensitivity to different functions. Yeah, this is the coarse graining. So essentially what you're doing is you start with a bunch of different lattice sites. Imagine just a lattice like a grid. There, each point on the lattice has a certain spatial coordinate. So it's just like a 2D, think of graph paper. Each one of those cells has some atoms in it. And think about a magnet. Those atoms have a spin up net or spin down net. Now, you take some sort of box or bubble and you average all the quantities together. That's called coarse graining. So now instead of on graph paper having 2x2 cells, we have 4x4 cells, and we're averaging what's happening out. This averaging is what they mean by integrating out. Essentially, we're taking averages over a large space or sometimes a large time, but in this case, large space because we're coarse graining. We're taking averages. Maybe those atoms are fluctuating all over the place, but if we average them over a large enough amount of space, we get less fluctuations and a more well-behaved, predictable kind of quantity. And that's what we mean by coarse graining. So we're taking bigger and bigger blocks where we coarse grain an average over. Yeah, see, that's kind of what I just said. Now, when you coarse grain, length scales change. We like to have natural units in physics. That is, we don't want a rescaling of arbitrary coordinates. Let's say we're measuring in inches or feet. That shouldn't affect the physics, right? What kind of ruler you have should not affect the physics. So what we do is we restore the natural units of the system by actually rescaling our coordinates. So essentially, even though the blocks are bigger, we want them to still be the same A, if that makes sense. See the spacing between the blocks in the left? We want the spacing on the right to not change just because we've rescaled the system. So we restore it by changing that. And the couplings will change when you do that. And you do this a lot of times. You zoom out, you rescale. You zoom out, you rescale. You zoom out, you rescale. And what we see is that certain things remain constant even though you're doing this. Right. Certain things will display the same statistical properties no matter how much we zoom out. Certain things won't. But we're more interested in the things that do, and that's what generates these universality classes. Remember the universal exponents I was talking about before. Near criticality, these are things that don't change as we zoom out in coarse grain. And to get a macroscopic quantity out of a microscopic quantity, you do have to coarse grain. To get magnetization out of like 10 to the 23 different electrons pointing different ways, you have to coarse grain that because that's just the nature of us. That's just the nature of our scale. We're not seeing individual atoms. If you look outside, you don't see atoms. You see a macroscopic average of those atoms. So physics has to be anthropic to a certain degree. It has to scale to our length because that's all we can do observably. So this RB is a linear transformation that is part of the scaling and the renormalization. And the idea is if you keep hitting this coupling space with it, it doesn't change. So these are things that are universal regardless of scaling. They're conserved in a sense under this particular transformation. This is where the actual universal exponents come from. If you zoom in on anything enough, even if it's curved, it looks linear. You can see this on the Earth right now. The Earth is actually curved. Sorry to disappoint the flat earthers out there, but it is actually curved. And you look outside and you see flatness. You see just linearity. So if you zoom in on something enough, it looks kind of like a straight line or just a plane. So that's what linearization means. A small enough change will create linearity. You're looking over a small enough distance. The idea is that everything is linear. And when it's linear, we use linear algebra. And when you use linear algebra, you have matrices. And matrices have eigenvalues and eigenvectors. And that's where these exponents come from. I don't think the details are too relevant here. I don't think anyone would be interested in them anyway, but you can absolutely read up on this if you are. Some things change, some things don't change. We're interested in the universal ones, the ones that don't change when we rescale, the things that are conserved. Okay, and this is particularly how the critical exponents come from eigenvalues. And the idea is near criticality, all these different quantities, like this is the correlation length xi here. They take this very simple form that's just the distance of the temperature from the critical temperature, like the freezing point, to the power of something, and that something are the critical exponents I keep talking about. Oh, and the critical exponents are related by certain relations. They're not independent. See, those are different theories, and they all have the same critical exponent. So the Ising magnet, the lattice gas, binary alloy, all of them have the same universality class. They're all in the same universality class, so they all have the same universality exponents. That's what this is demonstrating here. All right, good. So I think we have a pretty solid understanding of equilibrium phase transitions, and we're ready to generalize and move to non-equilibrium phase transitions as well. So quick refresher, key reminders. Very different microscopic systems like water, a magnet, some sort of percolation network or something like that. They're all different systems microscopically, we know that. But macroscopically, they have these same universal exponents, and that's what ties them into a universality class. And what I'm going to demonstrate for you here is that in non-equilibrium phase transitions, they're not going to seem like phase transitions. They're not going to be like water. They're not going to be like magnets. They're not going to be like chemical reactions or something like that. They're going to be things that seem very counterintuitive in terms of in terms of being a phase transition. But I'm going to demonstrate that they have these same mathematical signatures at criticality, and they also fit into the same universality classes. This is actually non-equilibrium phase transitions is actually kind of like a wild west frontier in physics right now. There's a lot of open questions, and there's a lot of interesting research, including mine, going on in this field. So that's a particular reason it's so fascinating, is that it's a new. It's a relatively modern notion that there are non-equilibrium phase transitions at all. So the idea is in an equilibrium phase transition, I showed you that we settle into these equilibrium positions. Ice, if the temperature is a certain way, or water is a certain way, systems want to be a certain way. In non-equilibrium phase transition, things are dynamic. Entropy is still being produced. There's no entropy production in equilibrium. Entropy is constant. Remember, we're trying to minimize it. In this case, entropy is changing. We break what's known as detailed balance. Detailed balance is that the probability of going from here to here is the same as the reverse of that, going from there to there. It's time reversible. So in equilibrium, that is the case. In non-equilibrium, it's not the case. Detailed balance is broken. But even though detailed balance is broken, what's still the same and what constitutes a non-equilibrium phase transition is something known as a stationary state. That is, you have this kind of operator that evolves the dynamics of the system forward in time. And this operator takes the system at t to the system at t+1 if it's operated on one time. It's a Hamiltonian in most systems, the expectation value of which is energy. A stationary state is one in which the evolution operator acts on it and it doesn't change in any kind of way. So essentially, nature's doing its thing and kind of computing or generating the new state, and that state is in a steady state. In other words, the evolution does not change where it is or anything like that. So we have a stationary distribution. Each microstate has a certain probability given by this. There's detailed balance. There's no net cycles. The probability of going from this state to this state is the same probability as the time reversal of that. And fluctuation dissipation is an interesting thing we can look at, but it has a well-known linear response in equilibrium systems. It's essentially this idea that if you perturb a system, it kind of comes back to itself, its own equilibrium. That's the dissipation part. And the fluctuation part is just if you leave it alone, it's naturally fluctuating. These things have a nice linear relationship in equilibrium. They don't in non-equilibrium. So probability currents are not equal to zero. Entropy is produced. FTD is generally violated. You need generalized relations, and transitions are seen. Right. So just kind of have a look at this animation for a little while. You see the probabilities of each of these are changing. So you have a probability configuration of being in a certain microstate at each given time. And over time, the probabilities of being in each state are changing. That's what this flow around the triangle represents. In an equilibrium state, that is not the case. They're fixed. They're e to the power of beta times the energy or the Hamiltonian operator, depending on what you're talking about. So each state has a probability that is fixed in time. There's a 60% probability to be here and a 40% probability to be here. And those numbers don't change. In non-equilibrium phase transitions, they do change. That's the idea of breaking detailed balance. So the idea is in dynamical non-equilibrium systems, what you're seeing as enforcing the steady state is not this Boltzmann distribution, or minimizing entropy, or minimizing the free, or maximizing entropy, or minimizing the free energy. The thing that's actually keeping these steady states in certain phases is what are known as Markov chains. That is, probabilities of going from here to here. The idea is you have a bunch of different states, and they're all linked by some probability of jumping from one state to another state. That's called a Markov chain. The idea is it has no memory. So the current state doesn't depend on n-1 or n-2 or n-3 states. It depends only on the current state, what the probability of jumping to any given other state is. That's called a Markov chain. So you see, we have this thing called a master equation here. And that's kind of the version of free energy for non-equilibrium phase transitions. This is, don't worry about what this actually is, but it's the probability of being in a given state times the probability of jumping to another state, summed over all possible states. But what this is actually saying is the gain term and the loss term. There are two of them. That is, the gain term is the probability of stuff jumping into the given state, and the loss term is the probability of things jumping out of the given state. The idea is the change in time of the probability of being in a given state is that gain term minus that loss term. Pretty intuitive. That's called the master equation. So, yeah, it's the same slide. I don't know why it's not advancing. Okay, so one of the simplest non-equilibrium phase transitions is what's known as a random walk. And it's kind of what it sounds like. It's sometimes called the drunkard's walk. It's Brownian motion, essentially, if you're familiar with that. The idea is you have some person or some particle or something, and it has a 50% chance of going forward and a 50% chance of going backwards. That's why it's called the drunkard's walk, because if you imagine a drunk guy kind of stumbling around, the idea is he has a probability to be here, or a probability to go backwards or forwards. And after a long period of time, the average position is obviously zero, but the average variation is non-zero. So this is the coarse graining that we talked about before. It's subject to these conditions here, and you essentially get this partial differential equation, which is the diffusion equation. The diffusion equation is essentially if you spray perfume in a room and it slowly spreads out throughout the room, that process is diffusion. So what you essentially get is dynamics that look like diffusion over time in the drunkard's walk. So you make it into a continuum version of that. That's sort of what's happening as animation here. You see each of these bars is the discrete probability, or the discrete step. So if you have a drunk guy wandering back and forth, each of his steps is one step. It's a discrete quantity. Whereas if you take averages over time, you can make it into a continuous function of time. So that's kind of going back to this coarse graining we were talking about before. So we see this pattern again. We're going to coarse grain the drunkard's walk. So how do we do it? This is the actual math behind it. You can kind of just study it if you like. The idea is that the master equation that I showed you before looks like this particular form in the case of the drunkard's walk. The probability of being in a certain position at a time plus a little change in time is equal to 1/2 the probability of it being at that same position minus one lattice step, or the size of a step. If you imagine the size of the guy's shoe when he's wandering around drunk, that's the lattice size. That's this A. Plus X plus A, in other words, being one step forward. So that's what we want. We Taylor expand it, and then we put everything in, and we get this diffusion thing here. And this diffusion thing here has a critical exponent to it, or it's where the critical exponent comes from. So this is, again, mean field. We have these kind of fixed points in this slowing down. When you renormalize, certain universality quantities remain, and they kind of converge to one point. This was known as a driven lattice gas. You can think about it as a flow of traffic because, again, they mathematically follow the same signatures. But you can think of A as the rate at which cars are entering the highway. And you can think of alpha, and you can think beta as the rate at which cars are leaving the highway. If we vary these things, we'll see different phase transitions. That's kind of the idea. Now, at one position, only one particle could be at a certain lattice site. That's the same thing as only one car can be at a certain position on a highway. Otherwise, you have a car accident. That's what this exclusion means. And you see there's a steady current that's defined by the parameters. So this is what's known as an absorbing state. Certain systems have what's known as an absorbing state. That is, once you go into that state, you're stuck there forever. If you think about a pandemic spreading throughout a population, if everyone dies, that's an absorbing state. Everyone's dead. The disease can't spread anymore. Nothing changes in that system. Absorbing state. This is the same thing that we said before about the Master equation. Yeah, we kind of went over this. There's some redundant slides in this. Trajectory ensemble. Not interesting. Large deviations. Yeah, I mean, kind of said this. Okay. At this stage in the presentation, I'm going to sort of show you a little zoo of non-equilibrium phase transitions. Some of the more interesting ones, famous ones. DP is the most famous one, directed percolation. That's also the simplest non-trivial one, directed percolation. You can see here that we have this master equation continuized here. It looks like the diffusion equation, but it has some other terms in it. This PT is the probability of, I believe it's the activity probability. That is the probability of how many particles are active on a given lattice at a given time. Whereas lowercase pt, possibly rho, is the probability of a given lattice being occupied. You notice these universal exponents here, alpha and delta. You see that they have these universality classes. Remember what we were talking about with renormalization, universal exponents? Those two are universal exponents. Then we're going to talk about chromatosynchronization, which my favorite application of that is fireflies. But essentially, you have this kind of these coupled oscillators here. Think about sine. Sine is just a wave that goes like this. So you can think about it as an oscillator, like a weight on a spring, something like that. And the idea is that there's the actual oscillation frequency of the spring. It can go this fast, or it can go that fast, or it can go really slow. But the idea is there's a second term in there, which is on the right, which is where this sigma is. That's a coupling between them. So this oscillation will depend on this oscillation. As we couple them stronger and stronger and stronger, the oscillations will become closer to each other, and eventually they lock into phase. And you see, for example, with fireflies, which I'm going to show you, all the fireflies flash together. Whereas you'll see fireflies randomly like this if the coupling is too weak. Taste-up transport, that's the traffic thing I talked about. Self-organized criticality, that one's really fun. That's like avalanches and stuff like that. Directed percolation, DP. These are the critical exponents. This is how the critical exponents affect scaling of certain quantities. This is the correlation length. And this is the governing field theory when we coarse grain. So what's interesting about this is that very, very different models that have very, very different microscopic properties all kind of have these universalities in them. So this is directed percolation in action. You can see that it spreads out over space and time. And this each little line here is a time front. So the idea is you have a 1D lattice of different sites, and at each given time, certain lattice points are occupied and certain ones are not. The blue ones are the occupied ones. The rest are not occupied. So that's what DP looks like over time. And the reason it's called directed percolation, you probably heard about like in coffee machines, percolation or something like that. What percolation actually means is you have this kind of fluid medium and it's going through a porous membrane. So in terms of coffee, it's actually the water's coming through the coffee grinds. That's the percolation part. And you can imagine like water bouncing around, like almost like a pachinko board kind of thing. That's really what directed percolation is. So the idea is how would water penetrate a porous medium? It can go like a pachinko machine, right? Around areas where it's allowed to go, where there are actual like fissures in the porous media, like a sponge, pour sponge over water. Where does the water come out? That's kind of like directed percolation, right? All right, so yeah, I said I did my bit about mean field. Yeah, so at criticality, these things go through phase transitions, and at the criticality, like right on the cusp, like their quote unquote freezing point, they have this universal properties, these universal behaviors with these universal exponents that are defined by these universal exponents. So that's cool. So it is a phase transition actually. And it scales in a certain way. This is what I said before. It's the simplest non-trivial one. This is very cool. So this is what directed percolation can look like in a forest fire system. You see these different phases that it can be in. Think about this as ice, water, and water vapor. The subcritical, near critical, and supercritical. Same as ordered and disordered. Analogous to ordered and disordered in the equilibrium picture. So you can see in the subcritical picture, the forest doesn't completely burn down. In the near critical picture, some clusters of unburned forest are left that are disconnected. Notice this cluster of unburned forest is connected. That's the key differentiator between subcritical and critical. Supercritical, forest burns down. You can think about it in terms of epidemic spreads. You can think about it in terms of a lot of things, but I like forest fires the best here. Okay, good. So Next non-equilibrium phase transition, synchronization. I already talked about this. But the idea is, as I tune this coupling constant, K, you can think about K as sort of the temperature of the system. It's the control parameter. That's what I've been calling it. As I tune it, you can see that initially the phases are out of sync, and this is the net phase, the macroscopic quantity of the phase. See how they sync up like that when K gets big enough? That's essentially what we're talking about here. And I think this is the Firefly animation. Yes, it is. Fireflies, if there's no coupling between their oscillations, they'll just oscillate randomly. See how they all flash at their own little frequency? Let's strengthen K a little bit now. Let's strengthen K a little bit now. Okay, there we go. Ramping K. So this is coupling the oscillations more strongly and more strongly to each other. See that the green are in phase and the red ones are still kind of rebels. They're still outliers. They're doing their own thing. So this is when K is medium strong, when the coupling is medium strong between these guys. Now we're going to ramp up K a little bit more, and we're going to get them to all lock into phase because they're all very strongly coupled now. See, they're all flash in phase. Now, instead of K, if you imagine temperature and water going into different phases, from solid to liquid to gas, this is a phase transition. But this is a non-equilibrium phase transition. It also has phases. They're just more complicated and have dynamics. All right, see, everyone's locked into phase then. I don't want to do that. Don't want to do that. Yeah, sure, why not? Anyway, don't know what that was about. Okay, there we go. So the onset of synchronicity, this is how you actually calculate it mathematically. Not that interesting. I just said that. Topology is important, and the actual underlying network, the connections are important. Sync in real systems. Fireflies, the way your heart synchronizes its oscillations and beats. If you have a power grid, the frequency of the AC and the frequency of all those things will phase lock if the coupling strength is strong enough. So you see weak coupling versus strong coupling. It's pretty much what I just said. All right, TASEP, this is traffic. This is what it looks like. Just think about traffic, but there are other models of it. Yeah, so think of these cars on a highway. There's a shock front because things are exiting slower than they're entering. So you have stuff coming on at 0.8 and coming off at 0.3. That's way lower. So there's buildup. And there's just like a buildup of cars coming on, and they can't exit fast enough. So that's a certain phase. I think this is my TASEP animation. So these are different phases. The different colors are different phases. The entry rate is high, but cars are able to exit at a same or higher rate. So there's no pileups. Everyone can drive at the speed limit or whatever speed they like. Now they're not allowed to exit that quickly. This parameter of how fast cars come on versus how fast cars exit the highway, think of that as temperature. That's the control parameter. And it induces different phases. Mean field current, I went over mean field already. Boundary phase diagram. These are specifics that I had in for other audiences. I don't think you'll be that interested in them. All right, so this is exclusion transport. This is what it looks like over space-time. Yeah, car traffic, ribosomes, motors on microtubules, control knobs, that's the control parameter, and signatures. Self-organized criticality. Okay, I really like this one. The idea of self-organized criticality is you see it falls into another universality class with the characterized by these universal exponents. But remember, again, the universal exponents is near criticality when we're near the freezing point, or we're near the boiling point, or we're near a point where we're going to see a phase transition. We see these quantities scale simply with these power laws. That's kind of the idea of that. So self-organized criticality, if you think about a mountain and it's snowing, the snow slowly drives the mountain to a point where an avalanche is going to happen. And then the avalanche happens, and then the snow keeps piling up. And the idea is it's constantly on this critical edge, where it's constantly in a critical state where it's about to avalanche. So you see where we were. Self-organized criticality. Yeah. So this is a little animation in an overhead view. Think about it as snow piling up and then avalanching. And when it avalanches, it goes onto other sites. It spreads out. And then those other sites, if they're too highly piled, they avalanche, and that's a chain reaction. So that's really the interesting part, is these chain reactions. Right, this is an overhead view, and I have it stop and pause and explain the avalanche every time it happens. And notice it cascades to other sites. An avalanche is when you actually get a chain reaction. See how it goes to the secondary sites, and the secondary sites affect tertiary sites, and those affect quaternary sites, and it goes out. That's kind of the idea of an avalanche. Man, PowerPoint is like being very tough. Oh, wait, here we go. This is the 3D version. If you're actually on the mountain looking, it'll probably look like this. See, it's called a sand pile model, because if you think about a sand dune at a beach or something like that, it sort of settles into an equilibrium shape. And this is why it settles into that particular shape. There's no minimization of entropy. There's no force like gravity. This self-organizing criticality, this is the reason it settles into that particular shape. The same reason a mountain with snow on it looks the way that it does. Okay, so those are the four systems I chose to show you. This is kind of what you should take away from it. And here's some kind of extra reading for the particularly interested viewer who wants to do some deeper research on these topics, which I strongly encourage. They're fascinating. All right, great. So thanks for listening. I've been me, presenting to you happily. Hope you enjoyed, and come back for more videos.